Hello everyone. In this video, I am explaining discrete probability distributions. There are various discrete probability distributions. Here I take up binomial distribution. So before going to study about binomial distribution, let us first define what is Bernoulli distribution. See, most of the experiment which are dichotomous in nature. That means their outcomes can be classified as success and failure, because outcomes can be divided into two categories. One you can name it as a success, another you can name it as a failure. For example, tossing a coin. When you toss a coin, you will get either head or tail. Okay. So if you name as getting head as a success, then getting tail becomes a failure. Okay. Similarly, when you roll a die, getting 6. Suppose if you want to get 6, getting 6, if you name it as a success, then not getting 6 becomes a failure. Not getting 6, then this becomes a failure. So, if you have such experiments where you can divide the outcomes into two categories, one as a success, another as a failure, then such experiments come under Bernoulli trials, and the distribution, the probability distribution corresponding to such experiment are called as Bernoulli distributions. So, Bernoulli trial means Bernoulli trial. Suppose you have a random variable capital X. This X takes two values such that 0 and 1. 0 for failure, not getting the required value, and 1 for getting the required value, that is success. And probability of success you name it as P, and probability of failure you name it as Q. This is probability of success and this is probability of failure, Q. Or else you can name it as 1 minus P, because total probability should be equal to 1. That is the condition of any probability distribution. So, P of probability of X equal to 1 is a small letter p. Probability when X equal to 0 is equal to Q, which is nothing but 1 minus P. So, such a trial is called as the above experiment. This kind of experiment is called as Bernoulli trial, and the distribution of probability with respect to this kind of trial is called as a Bernoulli distribution. See, the Bernoulli distribution goes like this. A discrete random variable X, a discrete random variable X is said to follow the Bernoulli distribution with the parameter P if its probability mass function is given by p.m.f. You know that for a discrete random variable we have probability mass function, and for continuous random variable we have probability density function. Now we are studying the probability distributions of a discrete random variable. Hence, we have this probability mass function which is given by P of X equal to X, okay, which is equal to P to the power X into 1 minus P power 1 minus X when X equal to 0, 1 and 0 elsewhere. For all these values 0 and 1, this is how to get its probability value. Okay. In all other cases, its value is 0, which is nothing but here P to the power X into Q to the power 1 minus X. When X is 0, you will have a P power 0 into Q power 1. Okay, that is Q. When X is 1, you will have P power 1 into Q to the power 0, which is nothing but P. So, this kind of distribution is called as a Bernoulli probability distribution. If you write it in the tabular form, then you will get X is 0, 1. Then here when X is 0, it is 1 minus P. Probability is 1 minus P. When X is 1, the probability is P. Hope you got this point. When Bernoulli distribution is used when you have an experiment which is dichotomous in nature, means it has its outcomes can be categorized into two categories, one as a success, another as a failure. The probability of success is denoted as P and the probability of failure is denoted as Q, which is equal to 1 minus P. And that discrete random variable takes only two values, 0 and 1. 0 is for failure and 1 is for success. To count, the number of success is 1 here, number of success 0 here. So probability is given by p of x equal to 0 as Q and p of x equal to 1 as P. Okay, and this Bernoulli trial is used only for a single trial. When you have more number of trials, then we use binomial distribution. Bernoulli trial and Bernoulli distribution is used for a single trial. That is the difference between binomial distribution and Bernoulli distribution. Bernoulli distribution uses only single trial, that is tossing a coin once. Okay, or rolling a die once, like that. See, for example, if you toss a coin once, so tossing coin once. Okay, so let us take success as a getting head and let us define failure as a not getting head, means getting tail. Getting tail, Q. So what is probability of success? P equal to 1 by 2. Q is also equal to 1 by 2. Therefore, the Bernoulli distribution is given by x p of x. X takes values 0, 1. Here x takes only two values, 0 and 1. Because either it is success or it is failure. When x is 0 means not getting head, which is nothing but getting tail, which is half. X equal to 1 means getting head, probability of getting head is half. This is the Bernoulli distribution for the given random experiment. I can do like this because the given random experiment is having two categories of outcomes. One is success, another is failure. Now we have to find out mean of Bernoulli distribution and variance of Bernoulli distribution. So mean of Bernoulli distribution is given by equal to P and variance is given by P into Q, or you can write P into 1 minus P. Mean is the first order central moment, that is mu1. Variance is the second order central moment, mu2. Okay. Similarly, if you want a third order central moment, which is nothing but mu3, that is equal to, you can write mu3 in terms of the moments about origin, mu3 dash minus 3 mu2 dash mu1 dash plus 2 mu1 dash cube. Okay, I have already uploaded a video on moments, different types of moments. So watch that video to understand how to get this formula. This formula you have to remember. So finally, after substituting all this here, then you will get P into 1 minus P into 1 minus 2P. This is a third order central moment, mu3. Similarly, fourth order central moment, mu4, is given by P into 1 minus P into 1 minus 3P plus 3P square. That is using the relation between central moments and moments about the origin. Using that, I have substituted all this. So take one problem. Let x be a random variable having Bernoulli distribution with the parameter p equal to 0.4. Find its mean and variance. Okay. So it is having the Bernoulli distribution. So as per Bernoulli distribution, its mean is given by mean equal to p and variance equal to p into q. Okay. So mean is 0.4, variance is 0.4 into q, means 1 minus p, 0.4, which gives you 0.4 into 0.6. which is equal to 0.24. This is how to calculate mean and variance. This is all about Bernoulli distribution. So to apply Bernoulli distribution, you need to have Bernoulli trial. What is a Bernoulli trial? Bernoulli trial means it is an experiment. It is a random experiment whose outcomes can be categorized into two categories. Means if you have a experiment, random experiment, which is dichotomous in nature, which has answer yes or no type of answers for the outcomes, then we call such random experiments as dichotomous in nature, and hence we can apply Bernoulli, we can name that as Bernoulli trial. So when you have Bernoulli trial, the probability distribution of that Bernoulli trial is called as Bernoulli distribution. And this Bernoulli trial has the values for random variable as only 0 and 1, and 0 means it is for failure, 1 means for success. The probability of success is named as P, and the probability of failure becomes 1 minus P. And the distribution function is given like this, okay, and whose probability mass function is given this way. And for a Bernoulli distribution, mean is P and variance is PQ. Other central moments can be given like this, but these two central moments are important. Now let us see what is binomial probability distribution. See, binomial probability distribution is almost the same like Bernoulli probability distribution, but here number of trials is more than one. In Bernoulli probability distribution, you were taking only one trial. Bernoulli means it is only one trial, but here there are more than one trial. More than one trial. What does it mean? This is binomial distribution. Means here you had tossing a coin once. Okay. But in this case you will have tossing a coin n times, or suppose 10 times if I take, then you have to find out the probability distribution. For any random experiment, the conditions are there are finite number of trials, and those trials are denoted as n should be finite. See, for example, tossing a coin 10 times means n equal to 10. Okay. The trials must be independent. The trials are independent. Means I plus 1th trial should not be dependent on the ith trial. For example, tossing a coin 10 times. Every toss is a fresh toss. Correct? No. So it is kind of independent toss. It doesn't change the probability of success. Correct. Now, such trials are independent trials. See, suppose if you are picking a card from a pack of 10 cards with the replacement, then each trial is independent. Without replacement, if you write, then the trials are not independent, because for the second trial, only 9 cards available. For the third trial, only 8 cards available. So, probability of success changes. And third condition is that the probability of success remains same in every trial. Okay. So you can name this as a fourth point. Third point is that the outcomes can be divided as success and failure. So outcomes as success and failure, divided as success and failure, means two categories. This is the basic condition of Bernoulli trial. Okay, the same will apply for binomial the probability distribution as well. Binomial probability distribution is a kind of general case of Bernoulli trials. Here more number of trials, there it was only one trial, and the probability of success remains same in every trial. It doesn't change because of this independent of trials. So if all these conditions are satisfied, then we apply binomial probability distribution for the given random experiment. See, for example, take the random experiment as tossing a coin 10 times. How many number of trials? 10 number of trials. And I would like to find the probability of getting getting 3 heads. Okay. So here getting 3 heads, that is my requirement, but success can be defined as in single trial. You think of that in a single trial. So in a single trial, if you are getting head is a success. Getting head. So what is the probability of success? Not for all trials you are finding. Only concentrate on the single trial. So in a single trial, when you toss a coin once, what is the probability of getting head? 1 by 2. What is the probability of getting tail? 1 minus 1 by 2, which is 1 by 2. Okay, we got the probability of success, probability of failure. In the second toss also, the probability of success is same as probability the before, correct? No. So there are finite number of trials, that condition satisfied. The trials are independent. Every toss is independent of its previous toss, and outcomes can be categorized as success and failure. Yes, getting head is a success, getting tail is a failure. Then probability of success remains same in every trial. So when you toss a coin once, probability of success is half. When you toss a coin second time, again its probability is the same, half. So it remains same. So in this kind of experiment, I can use binomial distribution, binomial probability distribution. Now therefore, how to define the distribution function for this? That is probability mass function for this discrete random variable. Let x be this discrete random variable which satisfies the conditions for binomial distribution, means there are all these conditions. Then its probability mass function is given by p.m.f is given by p of x equal to x, which is equal to ncx q to the power n minus x into p to the power x, where x is from 0, 1, 2 and so on up to n, 0 elsewhere. So you have to remember from 0 to n how many, that is important, how to remember the formula. So this is the main formula, ncx q power n minus x into p power x. What is n? Number of trials, and what is p? This is the probability of success. How you define success? Based on that, probability of success. And what is q? Probability of failure. And what is the small letter x? Number of success. That is required. What is asked in the question, based on that x changes. If we want 3 success, see, suppose here getting 3 hits, so x, small letter x equal to 3. We want 3 successes. Success is defined as getting head. How many successes? 3 successes. If you want to get 4 hits, then x becomes 4. How many values x can take? 0 means no success, 1 means 1 success, 2 success, so on up to maximum it can take n successes. So this formula you have to remember, and the corresponding table if you write. The x and p of x, 0, 1, 2, 3, 4, so on up to n. This becomes nc0 q power n minus 0 into p power 0, means it is nc0. nc0 is always 1 into q power n. The final answer is q power n. Then nc1 q power n minus 1 into p power 1. These are nothing but the terms of the binomial expansion. Binomial expansion a plus b whole power n. You might be knowing nc0 a power n plus nc1 a power n minus 1 into b plus so on up to finally ncn into b power n. That's why the name binomial probability distribution. These are the terms of the binomial expansion of p plus q whole power n. nc0 q to the power n plus nc1 q to the power n minus 1 into p plus so on up to plus finally ncn, then we have p to the power n. So same, x equal to 2 means nc2 q power n minus 2 into p square, so on up to finally ncn into p to the power n. This tabular form gives you the binomial distribution of given random variable x. Here you can write this as q plus p to the power n. So it's q plus p to the power n. The binomial expansion of this is same as the probability distribution of the variable x, hence that is called as binomial distribution. And binomial distribution of a random variable x is denoted as b of n comma p, where n and p are parameters. N means number of trials, p is the probability of success. It is denoted as b of n comma p. See, here is the first problem. An unbiased coin is tossed 6 times. So here number of trials equal to 6. Find the probability of obtaining. So there are total 6 sub questions. So n equal to 6. Okay, because coin is tossed 6 times. Usually when a coin is tossed twice, then you will have 2 to the power 2, 4 outcomes. Thrice means 2 to the power 3, 8 outcomes. 6 times means 2 to the power 6. That many outcomes you have to write if you are going with the usual method. But these trials are independent and there are finite number of trials, and here you are exactly 3 heads, less than 3 heads, more than 3 heads means getting head, you can name it as success. Therefore other outcomes come under failure. You can divide the outcomes into success and failure, and probability of success remains same in every trial because the trials are independent. Hence these trials are Bernoulli trials and there are more than one trial, hence this comes under binomial distribution. That is the use of binomial distribution. 6 times when a coin is tossed, then in that case you can't write the whole sample space. So it has 2 to the power 6 elements. But this helps you, binomial distribution helps you to simplify the work. Number of trials equal to 6. Everywhere we need to find out heads. So success you define as getting head. So getting head. Failure is therefore getting tail. So probability of success in a single trial you find out. When you toss a coin once, what is the probability of getting head? 1 by 2. There are 2 outcomes, 1 head, 1 tail. So 1 by 2. Q equal to probability of failure is 1 by 2. Okay. Therefore the probability distribution is given by probability mass function. First ncx q power n minus x into p to the power x. So n is 6cx and q is 1 by 2 to the power 6 minus x into 1 by 2 to the power x. Because probability of success and probability of failure same in this case, so I can simplify this as 1 by 2 to the power 6. Because a power m is a power m plus n, minus x plus x cancels, 1 by 2 to the power 6. So this is your probability mass function. Now go to the questions 1 by n. X means, small letter x means what? Number of success. That changes based on our requirement. So in the first case exactly 3 heads means small letter x equal to 3. Less than 3 heads means x is less than 3. So less than 3 means x equal to 0, 1, 2, like that. So let us do that 1 by 1. So first one, exactly 3 heads. So what is the probability of getting exactly 3 heads when you toss a coin 6 times? So it is p of x equal to 3. Put small letter x equal to 3. 6c3. 1 by 2 to the power 6. This is fixed constant. Only this value changes. What is the NCR formula? N factorial by n minus r factorial into r factorial. So as per that formula, 6c3 equal to 6 factorial by 6 minus 3 is 3 factorial into 3 factorial. So 6 factorial means it is the product of first 6 natural numbers. Therefore you will get here 6 into 5 into 4 into 3 factorial divided by 3 factorial means 3 2s are 6 into 3 factorial. This 3 factorial cancels, 6 cancels, 5 4s are 20. So this is equal to 20 into 1 by 2 to the power 6. So you can simplify 20 by 2 to the power 6 is 64. So after simplifying this, you will get the final answer as 5 by 16. 4 5s are 4 16s. Okay, so exactly 3 heads equal to 5 by 16. Probability of getting exactly 3 heads. Next, second question is less than 3 heads. So probability of x is less than 3. So less than 3 means how many values x can take? 0, 1, 2. Because a small letter x takes values from 0, 1, so on up to n. So it is 0, 1, 2, so on up to 6. N is 6 trials here. So now you have to find out probability of x equal to 0. Then add probability of x equal to 1 plus probability when x equal to 2. So when you add all these 3, you will get probability of getting less than 3 hits. Okay. So probability of x equal to 0. So the formula is this: 1 by 2 to the power 6. 1 by 2 to the power 6 means 1 by 64. So 1 by 64 is there in every term. You can take that common. Then 6c 0 plus 6c 1 plus 6c 2, because small letter x equal to 1, 2 and 0 accordingly. 6c x. So this is equal to 1 by 64 into nc0 is always 1 plus 6c1 is 6. You can check with that formula, plus 6c 2, 6 factorial by 6 minus 2 means 4 factorial into 2 factorial. 6 into 5, 4 factorial cancels by 2. 2 3s are 5 3s are 15. 15 plus 6 20. 1 plus 1 22 by 64. So that gives you 11 by 32. This is the probability of getting head less than 3. Okay. More than 3 heads. So more than 3 heads means a third question now. Probability of x is greater than 3. So greater than 3 means probability of x equal to 4, 5, 6. Okay. So probability of getting heads more than 3 means 4, 5, maximum 6, because there are 6 trials. So this is same as 1 minus probability of x equal to 0, 1, 2, 3. Okay. Because the total probability is 1, 2, 0, 1, 2, 3, 4, 5, 6. Total probability is 1. 1 minus, if you subtract this, then you will get the value. Why I have done this? Because otherwise I have to find out individually. That is also fine. You can find x equal to 4, x equal to 5, x equal to 6 individually. But I already have this value here, 11 by 32. Plus I have to just find out probability at x equal to 3, because till x equal to 2 I have already found this. Now I have to find out only x equal to 3. So 11 by 32 plus 1 by 64 into, put 6c3. Okay, 6c3 value 6 factorial by 6 minus 3 factorial into 3 factorial, which is 6 into 5 into 4 divided by 6. 5 4 so 20. Just now we calculated 20 by 64. 1 minus 11 by 32 into 20 by 64. So let us simplify this. 1 minus, this is 64, 22 plus 20, that is 42 by 64. Then 64 minus 42, that gives you 22. So this is 22 by 64. So 22 by 64 after simplification, that also you will get it as 11 by 32. So for the next one is also, it is 11 by 32. Even if you do x equal to 4 plus x equal to 5 plus x equal to 6, you will get the same thing. Next question is at most 3 heads. So at most 3. At most 3 means maximum 3. X at most maximum 3 should not be more than 3. X is less than or equal to 3. So that is probability of x equal to 0, 1, 2, 3. Okay. So it is same as x equal to 0, 1, 2 I just now found out, plus probability of x equal to 3. Adding all this. This you got it as 11 by 32. Correct? No. 11 by 32 plus probability when x equal to 32, x equal to 3 is 20 by 64. 20 by 64. So this gives you 64 here. This is 42 by 64, which is nothing but 21 by 32. This is the answer. See the second problem. The probability of a man hitting a target is 1 by 4. He fires 5 times. What is the probability of his hitting the target at least twice? So here a man fires 5 times. So n equal to 5. Number of trials equal to 5. And these are all Bernoulli trials. More than one trial means you have to go with the binomial probability distribution. And they had given he hits the target or he'll not hit the target. So success and failure, two outcomes are there. So probability of success is hitting a target, and the probability of hitting a target is 1 by 4 already given. So q equal to 1 minus 1 by 4, 1 minus p, that gives you 3 by 4. Q is 3 by 4, p is 1 by 4, n equal to 5. You have to find out what is the probability of hitting target at least twice. So we have this p of x equal to x as the formula, probability distribution, probability mass function, q power n minus x into p to the power x. Now here probability of hitting the target at least twice, so minimum twice or maybe more than twice. So that is the meaning of at least, greater than or equal to 2. So this is nothing but probability of x equal to 2, 3, 4, 5. Maximum is 5 because he fires 5 times. So you can find out values individually, or else this is same as finding 1 minus p of x equal to 0 comma 1. Here you need to find out just 2 values, otherwise you have to find out here 4 values. So because sum of all probability is equal to 1, so here like this, p of x equal to 0 plus x equal to 1 plus so on up to x equal to 5, that is equal to 1. Sum of all probabilities equal to 1. Now I want these 2, 3, 4, 5, which is same as 1 minus p of x equal to 0 comma x equal to 1. So let us find out only for x equal to 0 and x equal to 1. So n is here 5, 5c is 0, q is 3 by 4 to the power 5, then 1 by 4 to the power 0 plus 5c1, 3 by 4 to the power 4 into 1 by 4 to the power 1 as per the formula. Now let us simplify this. 1 minus 5c0, nc0 is 1, 3 by 4 to the power 5 plus 5c1 is 5, use the formula if you want, then 3 by 4 to the power 4 into 1 by 4. Okay, now you need to simplify it further, that is you take 3 by 4 to the power 4 common, then here remains 3 by 4 plus here 5 by 4, that is 8 by 4, which is 2. So this equal to 1 minus 2 into 3 by 4 to the power 4. Let us simplify this. 1 minus, this is 2 into 3 to the power 4, that is 81 divided by 4 to the power 4, 256. So simplify this. This is equal to 256 minus 162 by 256. So this gives you, and here 94 by 256, which is nothing but you can still simplify this, 47 divided by 128. This is the final answer. Probability of his hitting the target at least twice is equal to 47 by 128. Here we applied binomial distribution because more than one trial and it satisfies all the conditions of Bernoulli trials. Probability of success is given. We found probability of failure. We used the probability mass function of binomial distribution, hence we got the value. Now see next problem, third problem. Here it is given, let x and y be two independent random variables such that x is having the binomial distribution with parameters n as 4 and p as 0.7, and y is a random variable with binomial distribution having the parameters n as 3 and p as 0.7. You have to find probability of x plus y less than or equal to 1. So we know that when x and y are two independent random variables which follow binomial distribution, then x plus y also follows the binomial distribution with the parameters 4 plus 3, probability of success same. The condition is x plus y follows the binomial distribution with parameters n1 plus n2, p only when the probability of success remains same in both distributions, then only this x plus y can be combined, otherwise you can't combine. So n1 plus n2 you can do. Now here n1 is 4, n2 is 3, so 4 plus 3, x plus y follows the binomial distribution with parameters 7 and 0.7. n is 7 and probability of success is 0.7. What is asked? P of x plus y less than or equal to 1. So this is P of x plus y less than or equal to 1 means which are the possibilities? 0 and 1, no other possibility. So probability of x plus y equal to 0 and probability of x plus y equal to 1. So x plus y equal to 0 means here you will get, so 7c0, p is 0.7, so q is 0.3, 1 minus 0.7, 0.3, so 0.3 to the power 7, then plus 7c1, 0.3 to the power 7 minus 1, 6 into 0.7. You have to simplify this. So here 7c0 is 1, so 0.3 to the power 7 plus 7c1 is 7 into 0.3 to the power 6 into 0.7. So 0.3 to the power 6 if you take common, then you'll get 0.3 plus 7 into 0.7. So once you simplify all this, the final value will be 0.0037908. So this is the answer. So this happens because x and y given as two independent random variables with the binomial distribution having the parameters n1p, and here y is a random variable with the binomial distribution having the parameters n2p. If the probability of success is same, then only you can write x plus y with a binomial distribution having parameters n1 plus n2 comma p. Now next is moments of binomial distribution. The mean of a binomial distribution is given by n into p. N is number of trials and p is the probability of success. You know that. Now these are all central moments. So central moments, I just give you the central moments here. First central moment, you know that it is always equal to 0, and the second central moment is the variance. So here variance is given by n into p into q. Okay. Third central moment mu3 is given by npq, which is q minus npq into q minus p. Mu4 is npq into 1 plus 3 into n minus 2 into p into q. Okay, the textbook contains everything, that derivation, how did you get all these formula. I just give you the formula for mean and variance, how to find out mean and variance under binomial distribution. Mean is given by np, variance is n into p into q. And one more thing is, we know that probability, q is the probability. Is it a probability of whether it is probability of failure or success, probability value always greater than 0, less than 1. So what happens here? Q is less than 1. Now multiply both sides by np. npq is less than np. What is npq? Variance. So variance is less than np means mean, or you can say mean is greater than variance. So for a binomial distribution, this is always true. Binomial distribution, mean is always greater than the variance. And variance is given by sigma square equal to npq. Therefore, sigma equal to square root of npq, which is nothing but standard deviation. Standard deviation is given as square root of npq. Now let us see one problem. See, for a binomial distribution, with p equal to 1 by 4 and n equal to 10, find mean and variance. So find mean and variance. So you know that for a binomial distribution, mean is given by n into p and the variance equal to npq. So n is here 10, p is 1 by 4, so 10 by 4 means 5 by 2. And variance is npq. np I got it as 5 by 2 and q is 1 minus p. Okay, 1 minus 1 by 4, which is 3 by 4. So here you write 3 by 4. So this gives you 15 by 8. So answer is 15 by 8 for variance. Next, one more problem. The mean and standard deviation of binomial distribution are mean equal to 4 and standard deviation equal to 2 by root 3. Okay, you have to find probability of x greater than or equal to 1. So what is given here? Mean is given. Mean means NP is given 4. Standard deviation means the square root of NPQ is given 2 by root 3. We want NPQ square on both sides. NPQ equal 2 square is 4 by root 3 whole square is 3. Okay, we have NP equal to 4. Substitute here. 4 Q equal to 4 by 3. So 4 cancels. You will get Q equal to 1 by 3. If Q is 1 by 3, what is P? 1 minus Q. That is 1 minus 1 by 3, which is 2 by 3. So now we want P of X. Okay, greater than or equal to 1. So we got all these values. N I need. N is 4 by P. That is 4 by 2 by 3. So this gives you 3 goes to the numerator. 2 1s are 2 2s are 6. N equal to 6. Probability of x greater than or equal to 1 means x 1, 2, 3, 4, 5, 6. You have to find all these values. Instead of that, you can do 1 minus probability of x equal to 0. Because starting from 0 to 6, sum of all probabilities must be equal to 1. But I want all these sum, so it is same as 1 minus p of x equal to 0. So 1 minus binomial distribution, therefore 6c 0 q to the power 6. Q is 1 by 3 to the power 6. So this is equal to 1 minus 6c0 is 1 by 3 to the power 6. So which is equal to 1 minus 1 by 729. So this is equal to 728 by 729. So this is the probability of x greater than or equal to 1. See now coefficients of skewness and kurtosis. So we know that beta 1 is given by mu 3 square by mu 2 square. We are finding coefficients of skewness and kurtosis for binomial distribution. As per the formula, we got here mu 3 and mu 2 values. So these values you have to substitute here. Okay, after substituting, this is mu 3 square by mu 2 whole cube. So you will get q minus p whole square by npq. This is beta 1. Beta 2 is mu 4 by mu 2 square. So substitute those values of central moments, 3 plus 1 minus 6pq by npq. Then gamma 1 is square root of beta 1. This is a coefficient of skewness and this is coefficient of kurtosis, which is 1 minus 2p by root npq. Gamma 2 is beta 2 minus 3, 1 minus 6pq by npq. So these formulae you have to remember to get the coefficient of skewness and kurtosis for binomial distribution. See one problem. The mean of a binomial distribution is 30 and standard deviation is 5. We know that mean is equal to NP, which is given as 30, and standard deviation square root of NPQ equal to 5. You have to find the values of NP and Q. Okay, NPQ equal to square on both sides 25. NP is 30. Q equal to 25. So Q equal to 25 by 30, that is equal to 5 by 6. So once you got the value of P equal to 1 minus Q, 1 minus 5 by 6, which is equal to 1 by 6. So now substitute. N is don't know. P is 1 by 6 equal to 30. N equal to 180. So we got values of N, P and Q. Next, the second question is moment coefficient of skewness. Coefficient of skewness is given by beta 1 is equal to mu 3 square by mu 2 cube. Mu 3 square by mu 2 cube. Okay, then we want gamma 1, coefficient of skewness. First, for that we need beta 1. So for finding beta 1 we need mu 3, mu 2. So let us find out mu 2 and mu 3. Mu 2 is given by, as per the formula here, mu 2. This formula you have, substitute here, mu 2 and mu 3. Mu 2 is variance, so that is 25 npq, which we got it as 25, and mu 3 is equal to npq into q minus p, that is equal to 25 into q minus p. 5 by 6 minus 1 by 6 is 4 by 6. So after simplifying this, we'll get 50 by 3 because this is 2 by 3. Now substitute those values here. Mu 3 square. So mu 3 square, that is 50 by 3 whole square. 50 square by 3 square whole divided by mu 2 cube. 25 cube. So after simplifying this, we will get 4 by 225. This is beta 1. Therefore, moment coefficient of skewness is, so coefficient of skewness, moment coefficient because it is in terms of moments. Coefficient of skew1 is gamma 1, which is square root of beta 1, which is equal to 2 divided by 15. Take the root of 4 by 225. Next, similarly, I need now beta 2. So I will write here. See, I'll write here. Beta 2 equal to, use this formula, 3 plus 1 minus 6 pq. 3 plus 1 minus 6 pq, this together, divided by npq. This is equal to 3 plus 1 minus 6 into p is 1 by 6, q is 5 by 6, divided by npq is 25. So after simplifying this, you will get this value as 3 plus 1 by 150. We want gamma 2, coefficient of kurtosis, which is beta 2 minus 3. So you will get this value as 1 by 150 because beta 2 equal to 3 plus. So beta 2 minus 3 is 1 by 150. So this is greater than 0, positive value. Therefore, you can conclude that curve of the binomial distribution is leptokurtic because gamma 2 greater than 0 means curve is leptokurtic. And here it is positively skewed because this value is positive, and skewness is very less because in terms of 0 point some value you will get. So this is how to find out coefficients of skewness and kurtosis for a binomial distribution. These are the formulae to be remembered. Now let us see what is fitting of binomial distribution. See here, suppose you have observed data. This is by doing the experiment you got the observed data. This is obtained, observed data is obtained from repeated trials of a given experiment. Suppose if you are tossing a coin 10 times tossing a coin, and you are performing this experiment and you are recording the observed values. So that is called as observed data. Okay. On the basis of observed data, we find the theoretical or expected frequencies corresponding to each value of the binomial variable. We have the theoretical probability values, theoretical values or expected values. We call that as expected values. That is by our formula, whatever the usual formula we have for binomial distribution. Using that, we can get the theoretical values. So suppose when you have observed data and you want to calculate the theoretical values, that is expected values of the same experiment, then in that case, whatever the probability distribution we fit into the given data is called as fitting of binomial distribution into the given data. So we know the binomial distribution, how the binomial distribution is. Binomial distribution has the probability mass function p.f. p.m.f as p of x equal to x ncx q power n minus x into p to the power x, where q is a probability of failure and p is probability of success, x is number of success, n is number of trials. Okay, this is the probability mass function of binomial distribution. Okay, this is the theoretical way of calculating the probability distribution of a binomial variable. Now, to fit binomial distribution into the observed data, first step is you have to get a recurrence relation for the probabilities of binomial distribution. For probability, recurrence relation means calculating the next value of the I plus 1th value of the probability using the ith value. So that is given as p of x plus 1 equal to n minus x divided by x plus 1 into p by q into p of x. This is the recurrence relation. So this is obtained using this same formula only, replacing x by x plus 1, then dividing. This is how we obtain the recurrence relation for probability. Means probability of x plus 1 is calculated using the probability of x. So this is the first step. First recurrence relation for probability we have to get it. Then so this relation helps you to find the probability of binomial distribution. Initial probability you need. Initial probability means at x equal to 0. Okay, you have to take p of 0 at x equal to 0 means here nc0 is 1, q power n minus 0 into p power 0. So it is q to the power n. At x equal to 0, initial probability is q to the power n, that is using this formula itself. So p of 0 equal to q to the power n, then p of x equal to 1 now next. Okay, p of 1 equal to n minus x by x plus 1 p by q into p of 0. Using that relation you have to find out p of 1. Then using p of 1 find p of 2. Using p of 2 find p of 3 and so on. Okay. Now after doing this, your second step is you have to get binomial frequency distribution. Binomial frequency distribution. See, frequency distribution is different, probability distribution is different. Okay, so now we are calculating binomial frequency distribution. Okay, so what is this binomial frequency distribution? Suppose you know that. Now you know that if you have a random experiment with n trials, then the probability of x successes is given by ncx into q to the power n minus x into p to the power x. Okay, this is for n trials, where x is the number of successes. Now, if this experiment, random experiment with the n trials is repeated n times, repeated capital N times. So in that case, the expected or theoretical frequency of getting x successes is, so that is expected frequency of x success is given by f of x. It is denoted as f of x equal to n times p of x at x equal to x. You have to multiply the probability value with the capital M to get the expected frequency of x successes. So this is that formula. Probability is multiplied by capital N to get the corresponding expected frequency. Okay, so that is the meaning of binomial frequency distribution. Suppose, see, if you have a random experiment of tossing a coin 10 times. Okay, this is the random experiment where small letter n equal to 10. Now, if this experiment is repeated 20 times, okay, that is capital N equal to 20. Tossing a coin 10 times, this is treated as a single experiment now. This single experiment is repeated 20 times. So you just imagine that there are 10 people. 10 people are tossing a coin. So it is tossing a coin 10 times. So both are same. 10 people tossing a single coin at a time, as well as tossing the same coin 10 times, both will have the same sample space. So now if 10 people are tossing a coin at a time, then the same experiment is repeated 20 times. So here see, 10 people are standing like this. Now the first time, if they toss the at a time, then that is the first time they are doing. Second time means same 10 people have to toss the coin once again. So this way they have to do it 20 times. Okay, in that case we get the expected frequency of getting x successes. So it is denoted like this, which is multiplied, probability value is multiplied with capital N. That gives you expected frequency of x success. Okay, now later, third step, now you have to fit binomial distribution. Fit binomial distribution. See, when you have the observed data, you have to find out mean from the given frequency distribution. So frequency distribution will be given to you. Frequency distribution. From that, find out the mean. Okay, then after finding the mean, you know that mean of a binomial distribution equal to np. You will get what is the value of p. Okay, after getting value of p, you get the value of q. Okay, after getting q, you can find out p of 0, q to the power n. Then you substitute it in the recurrence relation to get p of 1, p of 2, p of 3. Then you have to find out expected frequencies, that is f of 0, f of 1, f of 2. How to get expected frequencies? Multiply the probabilities with the capital N. So here also n into p of 1, n into p of 2, and so on. Okay. So in this way, the binomial distribution is fitted into the given data. This is called as fitting the binomial distribution, fitting of binomial distribution into the observed data. I'll explain this using an example. See, tossing 4 coins once, okay, at a time. Toss 4 coins at a time. Okay, that is repeated 200 times. Okay, and number of heads noted here. So getting heads, 0 heads in 15 tosses. They had conducted this experiment. Okay, there were 4 people standing, and those 4 people were tossing a coin at a time, which is same as 4 coins were tossed. Okay, so first time they toss at a time, that is the first trial. Then second time they tossed, third time they tossed, like this, so on up to 200 times this experiment is repeated. Okay, then number of heads out of these 200 times the trials get repeated. 0 means out of those 200 repetitions, out of those 15 were having no heads. Then 35 tosses had 1 head. Then 90 tosses had 2 heads. 40 tosses had 3 heads. 20 tosses had 4 heads. So that is given. This is the observed data. Now you have to fit a binomial distribution to these observed results, assuming that the nature of the coins is not known. Fit a binomial distribution to the above data, assuming that nature of coin is not known. Nature of coin means what? Whether it is biased coin or unbiased coin, we don't know. If it is unbiased coin, then probability of success is getting head is half. Probability of failure is also half. Nothing is mentioned, so we can't take directly probability of success getting head as a half. Therefore, what you should do is, now you have, this is the observed data. Somebody has conducted this experiment 200 times and they observed these values. When you add all these number of tosses, this is frequency. Okay, you will get 200. Okay, so now we have to fit a binomial distribution to this given data, and we have to compare what is our theoretical distribution value and what is the observed distribution value. Let us do that. How to do it? First, you have to list out what is n, small letter n and capital N. N equal to 4, capital N equal to 200 times the same experiment is repeated. First, let us find out the mean of the given frequency distribution. So, frequency distribution. So, this is number of heads, that is a random variable value, and this is f, number of tosses means it is frequency. So, we have the tabular column here. xf. X is 0, 1, 2, 3, 4. F is 15, 35, 90, 40, 20. Okay, then we need to find out the mean, means x into f. Okay, this is 0, this is 35, 180, 120 and 80. Then we need the sum of all these. Sum of all these comes out to be 415. How to find out mean? Mean equal to this summation of xi fi divided by capital N, that is the total frequency. So total frequency comes out to be 200. So this is mean equal to 415 by 200, which gives you 2.075. Okay, this is mean. Now we have to fit binomial distribution into the given frequency distribution. Therefore, we have to take mean as NP. NP equal to 2.075, because we know that for a binomial distribution, mean is given by NP. N we know 4, small letter n is 4. Using that, let us find out what is the value of P. So this gives you P as 0.5188. Once you got P, find Q as 1 minus P. Q comes out to be 0.4812. Okay, this is the value of Q. Once you got P and Q, probability of success and probability of failure, then you have to make use of that recurrence relation. So what is the recurrence relation? P of x plus 1 is equal to, this is the recurrence relation, n minus x divided by x plus 1 into P by Q into P of x. Now x takes the value 0, 1, 2, 3, 4. Maximum 4 coins tossed here. Correct. Now, so now I need to get the value of P of 0. How to get P of 0? P of 0 is nothing but Q power n. So in this case it is Q power 4. That is 0.4812 to the power 4. Okay, this is the value of P of 0. So this is equal to 0.0536. After simplifying, we get this value as P of 0. Now I need P of 1. P of 1 equal to n is 4 minus x is 0 now, divided by 0 plus 1. Then P is 0.5188 divided by Q is 0.4812 into P of 0 is 0.0536. Okay. So put x equal to 0, first case. Put x equal to 0. Then we will get P of 1. So simplify all these. After simplifying this, we will get P of 1 as 0.23115. 0.23115. Similarly, you have to continue like this. So for that, you need to write the tabular column. So the tabular column says here, number of heads, that is the random variable, that is capital X. Okay, then we have the recurrence relation, n minus x divided by x plus 1 into P by Q. Just make a column for this. We know that P of x plus 1 equal to n minus x by x plus 1 into P by Q into P of x. We know this value. Now we are not writing P of x here, just write this term P by Q. Then this is a P of x, column for P of x. Then expected or theoretical frequency, expected frequency or theoretical frequency, which is small letter f of x. So number of heads, here let me simplify. N is 4 minus x by x plus 1 into P by Q. P is 0.5188 by Q is 0.4812. After simplifying, we will get it as 1.07814. Okay, this is one column. So what we have here is, this is one column and this is another column. Then we have P of x. Then we have the expected frequency. Okay. Now x takes value 0, then it is 1, then it is 2, 3 and 4. Okay. X is 0. What happens? 4 minus 0 by 0 plus 1. Okay. Into this value, that comes out to be 4.31256. P of 0. What is the value of P of 0? P of 0 is nothing but q to the power n. Okay, P of 0 is q to the power n, and we got P of 0 as 0.0536. Then expected frequency f of x is what? N into P of x. Correct? No. So you have to multiply this value with capital N. What is the value of capital N? Capital N, 200 times it is repeated. So capital N equal to 200. 200 into this value gives you 10.72. 10.72. Round off this to an integer, which is 11. Now similarly, when x equal to 1, 4 minus 1 by 1 plus 1, 3 by 2. So 3 by 2 into 1.0, that gives you the value 1.61721. So now you need to find out P of 1. How to get P of 1? P of 1 equal to, using this relation, this expression into value of P of 0. So what we got the value of this expression here? We got the value of this expression as 1.61721. That is for x equal to 1. Now to get P of 1, we have to put x equal to 0. So for x equal to 0, what is the value of this expression? 4.3. So it is 4.31256 into P of 0 means this 0.0536. So after simplifying these two, we'll get 0.23115. Okay. Then multiply this with 200, that gives you 46.23. Round it off, which is equal to 46. Okay. Next we have to find it for x equal to 2. 4 minus 2 by 2 plus 1, that is 2 by 3. 2 by 3 into this value. So for x equal to 2, you will get this value as 0.071876. Okay. So now we need P of, here x equal to 1 over x equal to P of 2 we need, means x equal to 1. So for x equal to 1, what is the value of this expression? Value of this expression for x equal to 1 is 1.61721 into, you will get P of 1 now. What is P of 1? 0.23115. So that gives you the value 0.37382. 0.37382. So multiply this with 200, which gives you 74.76, which is nothing but 75. Okay. Next, similarly, for n x equal to 3, substitute here, put x equal to 3 and get its value. So that comes out to be 0.26954. Then you multiply this value 0.071876 by this value 0.37382. We need always the previous values we have to take. That gives you 0.26869, 51.73, which is nothing but 52. You can round it off. Next, for x equal to 4, 4 minus 4, this gives you 0. Okay, so this comes out to be 0. Okay, next, no values exist, therefore this is 0. Now multiply these two, 0.26954 and into 0.26869. So that gives you the value 0.0724. Okay. So multiply this value by 200 now. So that gives you 14.48, which is equal to 14. Okay. Now we got the expected or theoretical frequencies. So as per this, the theoretical frequencies are given 11, 46, 75, 52 and 40. What are our observed frequencies? Getting number of tosses. The 0 tosses we got 15. Here 0 tosses we got 11. Okay. So 1 toss we got 35. Here 1 toss 46. Next 75. Here it was 90. There is a difference because we are fitting binomial distribution into it. So here it is 52. Then here it is 40. Last one 20. And here it is 14. Approximately equal to. We are This is the possible best fit for the best binomial fit for the given distribution. So this is how we do fitting of binomial distribution to the given data. So remember, under fitting of binomial distribution to the given data, what we do is a collection of data is given to you. Okay, that is the observed data. They conduct the experiment and observe the values and write those in the tabular form. Okay. And this fitting of binomial distribution is applicable for Bernoulli trials repeated, the random experiment with the n Bernoulli trials repeated n times. That is, small n Bernoulli trials repeated capital N times. In that case, in such cases, we use the fitting of a binomial distribution. So here they had given number of heads and number of tosses. So first you have to do here, they have not mentioned what kind of coin it is it unbiased or biased. So we need to go with the finding the mean. Why we need to find the mean? Because we know that for a binomial distribution, mean is given by np. Small letter n already given, using which we can calculate p. Once p is obtained, you calculate q. After getting q, use this recurrence relation to find out the probabilities, expected theoretical probabilities. So once the theoretical probabilities are known, then theoretical frequency, expected frequencies are calculated using this formula, probabilities to be multiplied with capital N to get the expected or theoretical frequencies. So this is how we fit the binomial distribution into the given observed data. See the second question. 7 coins are tossed and number of heads noted. The experiment is repeated 128 times. So 7 coins are tossed means small letter n equal to 7, capital letter N equal to 128. Okay. So binomial fitting of binomial distribution is applicable when n Bernoulli random experiment of n Bernoulli trials is repeated n times. Okay, n means small letter here. Bernoulli trials, number of Bernoulli trials is denoted using a small letter n. Then the whole experiment of n trials repeated how many times, that is capital N. Okay, for such random experiment we have to fit the binomial distribution. So here the frequency distribution is given, number of heads and frequencies. This is the observed data. Okay, after conducting the experiment, this is the observed data. Now we have to fit our theoretical data to this given data. So fit binomial distribution assuming coin is unbiased. This is given now. Unbiased means what is the probability of getting head? Half. Probability of getting tail is also half. Okay, because unbiased coin means your normal coin. So in this case, what we should do is we have the values of p and q directly available. We need not find the mean of all these. We did that in the previous case because the coin was nature of the coin was not specified there. So we found the mean because mean we know that np equal to, we can equate it that, and hence we got get the value of p. But now p and q directly available, therefore you can directly go with the recurrence relation. P of x plus 1 equal to n minus x by x plus 1 into p by q into p of x. This is the recurrence relation. X equal to 0, 1, 2, 3 so on up to 7, because coin tossed, 7 coins are tossed, means coin tossed 7 times, both same, and that experiment is repeated 128 times. Now using this recurrence relation, we can now find out what is p of 0. P of 0 is q power n, which is q power 7. So this is equal to 1 by 2 to the power 7. We got the value of p of 0, which is nothing but 1 by 128, which is p of 0. Okay. Now we need the expected frequencies. Expected frequencies. So these expected frequencies are obtained by using the concept of binomial distribution. Binomial distribution helps you to get the expected frequencies, theoretical frequencies of that random experiment. So for expected frequencies, we have the tabular form, number of heads, that is capital X. Then we need one more column, n minus x by x plus 1 into p by q. Okay, keep it as it is. Then one more is p of x. Then your expected frequency, theoretical frequencies, which is nothing but n into p of x. F of x is n into p of x. So four columns you have now. Okay, let us find out one by one. So how many values x takes? 0, 1, 2, so on up to 7. So 7 values here. See, 0, 1, 2, 3, 4, 5, 6, 7. Okay. Now let us find out the value of this expression here. Okay, this expression simplifies as n equal to 7 minus x, we don't know, x plus 1 into p by q. P is half by half, that is nothing but 1. So you just have this expression, put x equal to 0 in the first case. So you'll get 7 by 1, which is 7. Okay, then here p of 0, we got it as 1 by 128 here. P of 0 is 1 by 128. Next, f of 0 is n into, that is 128 into 1 by 128, that is 1. Next, put x equal to 1 here. 7 minus 1, 6 by 2. 6 by 2 is nothing but 3. Then p of 1 I want now. P of 1, how to get p of 1? That is this value into p of 0. Okay. This value when x equal to 0. When x equal to 0, what is the value of this expression? 7. So I have to multiply these two. 7 into 1. P of 0. So I have to multiply 7 into p of 0. So 7 by 128 I have to do. 7 by 128. Okay, that is equal to 7. Once again multiply that by 128. Similarly, you have to now here put x equal to 2. 7 minus 5 by 3. So this gives you 5 by 3. Then here multiply these two. 3 into 7 by 128, which is 21 by 128, which gives you 21 here. Next, similarly 4, it is for 4, it is, this is for 0, this is for 1, this is for 2, now this is for 3, not for 4. Now for 3, this gives you value 1. Put x equal to 3. Then multiply these two. 5 into 21. So that gives you finally 35 by 128. So this is 35. Continue like this. For 4, you will get 3 by 5. For 5, you will get 1 by 3. Then for 6, you will get 7 by, for 6 you will get 1 by 7, and for 7 you will get 0. Okay, and accordingly here you will get 21 by 128. Next is no, here you will get 35 by 128 again, then 21 by 128, then 7 by 128, then 1 by 128. So here you will get again 35, 21, 7 and 1. Okay, so these are the expected values or theoretical values of frequencies. You can compare with the observed values. See, for 0, 7. For 0 it is 1. There is a difference. 1, 6. Here it is 7. Then for number of heads 2, frequency is 19 you got. Number of heads 2 means here you got 21. Almost same, at some values it differs. So this is how we fit the binomial distribution, and to we fit this binomial distribution to get the expected frequencies or theoretical frequencies of the given random experiment, where the random experiment is what kind of random experiment? Random experiment is repeating n Bernoulli trials n times. So that is how we define that random experiment. For such random experiment, we fit the binomial distribution.